All right. Now, let's see. So one thing that, well, we're actually doing pretty well on times in the overall schedule, in spite of today's late start. So that means we have time for any homework questions. I understand there's been some difficulties with homework 3. No, well, the one that was due earlier this week, yes.
I have a question.
Yes.
So we have a syllabus in your website and a syllabus in the Canvas. So like,
Yeah.
which one do we follow?
We're different. We're not supposed to. We're not supposed to be different.
I mean, is there? I didn't find like the midterm exam in your website.
Okay.
If it's there.
I've not put anything there for it. Okay, hold on. Just let me take a look. Okay. My short answer is that because it's to follow up with a website, because for all I know, something whatever's put on Canvas might just be. Well, okay, let me check the site now. Okay. Oh, sorry. I guess I'm not sure what happened with the site. I might have copied over from 460 and not updated. Okay, so I assume you're referring to the discrepancy of how the grade is determined. Yeah. So that is what's in Canvas.
Okay.
And so let me just resolve this right now, and that's just going to aggravate the hell out of me. Please let me know, are there any other discrepancies that I should be aware of?
Yeah, I think just that. The syllabus.
No, I mean, within the syllabus, there's a thing about the grades and how that's determined. Are there any discrepancies between what's on the site and what's on Canvas besides the grading determination? That's what I need to know.
Does that mean the lowest homework grade is not
Oh, no, I will still drop the lowest homework grade because they're so low. Okay, so I'll just take a couple minutes here to fix that now. Thank you for bringing it to my attention. Sometimes it takes too long to find out about these things.
I didn't even notice there was a syllabus in Canvas.
I forgot there was one in Canvas too. Even though I would have put it there from a document I handed out. It wasn't Canvas the exact document I handed out to you on the first day of class, which is definitely canon. So, okay. All right.
Not what you handed out in class. If you
Yeah. So that's in Canvas. Okay. Okay, so that's taken care of. Now, but yes, are there any? Because not many people have turned in homework 3. I'm aware of people still working on it, and I am pretty lax about these things, especially when we're talking a matter of just relatively short time late, and let's see. Well, yes. So really, it's not even half the class who has turned it in. So I'm pointing that out because that means that there's absolutely no shame whatsoever in asking a dang question about it, which I'm sorry you guys have been so horrible about. And whatever hang up is causing that, you need to get over it. I mean, it's forgive my bluntness, but it's time to grow up now. So, so if there are any questions, you know, if you're really gun shy, you can always ask them after class. Please do, or you can ask them now.
We got one.
Okay.
About the next assignment, do they need to go first?
Yes, I do. Yeah,
That's
but
fine.
I will handle that also.
You're welcome.
Okay. Really?
Well, we have one, but we can just need you to check it after class. Then we figure
Okay, that's fine.
Okay.
Yeah, because I mean, because we talked specifically about having some questions.
4.2,
Yeah.
that's the one that I think we finally figured it out.
Okay. All right.
So we just wanted to make sure that we're on the same page.
Okay.
This is a log.
Yes.
Yeah.
Yeah. So is it about the graph that you got?
Yes.
Yeah.
I got a straight line.
Okay, we got a straight line, but then you have to like change the ends each time. And then we finally got like a V.
A V?
Yes.
I got the.
We got a straight line and then we got something that didn't look like that.
Okay, that's really weird.
Yeah, I don't.
Okay. Okay. If you make sure that the ends that you choose are in increasing order,
They are.
and then make sure that the correct condition numbers match with the corresponding ends, it should not be a V. That's, and maybe, so we can talk about that after class. Now, I want to make a comment about the graph. Now, for a problem, I only asked produce a graph, but I want to say something about how you would interpret it. Since it's on a log scale, so you get some, yeah, you are supposed to get a straight line. So this is n, and this is the condition number in the 2 norm of A, and I'm going to put a subscript of n indicating it's the n by n version of this matrix. So how you can interpret this, since it's like a log scale, is you saw in your graph like powers of 10. So since it's a line, you can try to gauge the slope of a line by comparing like change in exponents on the y-axis and change in exponents on the x-axis. So let's suppose that the slope is equal to m, whatever that is. So I'm not going to tell you, just read it off a graph. So that means that the condition number of A as a function of n is proportional to n raised to the m, n raised to the m power. So this shows that because there's this exponential relationship, so that's how you interpret log-log graphs. And in fact, what you can do is, if you think, so like if I have a vector of n's and a vector of condition numbers, so I'm just giving them these names here, then what you can do is, if you think you figured out what the slope is and you want to confirm it, so you do hold on, so this freezes this graph in place, and then you do another log-log, and you plot n against n dot raised to the m power. And if you have the slope correct, you should get 2 parallel lines. Although, actually, I'm going to change this. I'm going to put an R here, and then I'll make this B. So it plots the first one in blue and the second one in red, just so you can tell them apart. Yeah. So then you can confirm the relationship between them. Again, I didn't require this in the problem statement, but and perhaps I should have, but whatever. Okay. Now, okay. So, any other homework-free questions at all? All right.
I was wondering if you could talk a little bit about the best way to approach 5.1.1.
5.1.1.
I think I understand what I'm supposed to do, but 326 was a long time ago, so.
Okay.
I think I was terrible.
Oh, okay. Okay, so in other words, like computing T.
I think I know how to compute T, but as far as getting the norm.
Oh, well, that's not something that would come up in 326.
Yeah, okay.
So
I wasn't sure because, like I said, it was a blur.
yeah. In fact, that would not have even been covered
Okay.
in 326 because they just don't cover much of anything.
Yeah.
So, it's like, yeah, this is your first linear algebra course. I keep making references to that, but this is it. So, all right. So, 5.1.1. The way you compute the infinity norm of a matrix, you can have MATLAB do all the work on that one. So you use the norm function, which by default uses a matrix 2 norm, but to get the infinity norm, you can put INF in quotes, and that'll tell it to use the infinity norm. Well, I think the quotes are not even required, but whatever. Okay. Yeah, so I'm looking for, what do you think will happen based on the norm that you get? Because we have this condition that an iterative method will converge if the norm is less than 1. It will converge if and only if its spectral radius is less than 1. Now, so one thing I want to remind you about is, a fun fact about eigenvalues. So the spectral radius of a matrix T is the maximum absolute value over, so this is real formal notation here. So you look at the eigenvalues and take the maximum and absolute value. Now to get the eigenvalues, all right, now, of course, the lazy way to get them is in MATLAB. So you can get, like I of T will just give you a column vector of the eigenvalues. But for this problem, it's a 2x2 matrix, and it's also going to have a nice structure to it. So I will point out that if the matrix is triangular, lower triangular or upper triangular, it does not matter, the eigenvalues are equal to the diagonal entries. So you can just take the largest of those. Okay. All right. Now, since there are some people still working on homework 3, I'm going to look through it really quick, or a list of problems, and see if there's anything I wanted to preemptively comment on based on anyone's experience with it. Okay. Okay. One thing, this is really an outgrowth of what I saw on when grading homework 2. Okay. there are a number of times when I'm looking at someone's code and I can tell just by looking at it, like, this is not going to run. There's going to be an error message, and now makes my job easier as far as grading is concerned. But so you can have some greater confidence that what you're turning in is going to be correct if you go ahead and run it on an example, and it works. So as an example, so suppose you have some function, like a function that you've written for an assignment. Like, for example, solve AXB, like from a last homework. That's meant to solve AX equals B. In a general case, you could do something like create a random matrix. Like, for instance, you create a random 5x5 matrix. I mean, you create a random column vector that has a compatible size. And then, well, I wouldn't use a vector symbol in MATLAB, but anyway. And you can check, like, first get the exact solution using backslash, and then you can call your function. And make sure they agree. If they do, then pretty much you're home free, assuming you also follow the problem directions, which we've talked about last time. Now, there are certain functions, like for certain cases, like there's problems that assume the matrix is upper triangular or symmetric positive definite. So to make certain types of matrices, so let's suppose I've made it, I've created a random n by n matrix just as a starting point, but that's a general matrix, and we need this matrix to have certain properties. So suppose I need it to be upper triangular. So you can use try u, and that will extract the upper triangular part. So like if that's what's required for the problem. Or I can use try L to extract the lower triangular part. Here's one, a tridiagonal. So what you can do is, if I use try U and try L together, so okay, what this will do is, first you take the lower triangular part, but you take everything below the first diagonal. In other words, the one above the main diagonal. So it's lower triangular plus one diagonal more. Then you extract the upper triangular part of that, keeping the first diagonal below the main diagonal. So these two functions together will zero out everything else. So what's left is a tridiagonal matrix. What? Yeah, this is a 5. Yeah. Okay. Another example. This is one of the homework 3 problems. You have a function to compute a Cholesky factorization. So if you want a matrix that is symmetric, positive, definite, so you go ahead and create a random matrix, and to make it positive definite, you can do this: A transpose times A. So as long as A is non-singular, which any randomly generated matrix is going to be, then A transpose A will be symmetric, positive, definite. So whereas if you make any general random matrix, that will not be. So then you can try your Cholesky function on it anyway and see if it fails, because in that case it should fail. Okay, so here's how you would check factorizations. Because there are functions in homework 3 to compute the LU factorization of a banded matrix. So for example, one of them was like your Cholesky function. G is Cholesky of A, then G is supposed to have a property that G times G transpose is equal to A. So you check A minus G times G transpose. And this should be roughly 0. I mean, there will be round-off error. But the point is you get some numbers that are like on the order of 10 to the minus 15. So essentially, they're 0. There's one like if you have a LU decomposition. So you can say, look at A minus L times U. That should be 0. So these are all things you can do, the types of things you can do to make sure your code works before you hand it in. So then I'm not looking at like, oh my God, what are we doing? So, right. When I was a software engineer, I had to test my code very fairly, even though we had people whose sole job was testers. But I had to at least do rudimentary testing to, and when I did and I got burned, then I got yelled at and it was very unpleasant. And yeah, so yeah, just take a little time to do this can help your code. And if you're wondering, I covered certain categories here, but if there's other categories I didn't cover, you can ask me about how to check those things. But here are some ideas. Okay. And was there anything else from this assignment? All right. Well, aside from what I already put in the hints, but be sure to, if you have any other questions, you can check me after class, and also, try not to wait until shortly before due date, because I give as much time as I do on these things for a reason. So, especially if there's something like, what if there's a mistake in a problem or something unclear about it? If I get the information out to you, all of you, sooner, then that'll make things easier for everybody. So, now the next assignment, homework 4, which is comforting to know that at least one of you has started. Okay, so that's due next week. So, I mean, if it's something where something has come up that has let it be swamped, like a modern test, so, no, that's okay. You just go ahead and take a little time. I'm not going to be all buttered about that, but I mean, yeah, just, do your best to keep up. But I know that these things happen. That can be quite traumatizing. Okay, so
we also have a modern test and this midterm on the same day.
really,
Yes.
Great. What wonderful information.
What day is that?
It's like
It's
like
27th.
Yeah. Modern test.
It's 2 weeks after, it's the Tuesday, 2 weeks after spring break.
Well, that is just
Okay.
very
So it's like
terrible.
I'm just throwing that out there. Yeah.
It's in March.
Is that our test too?
As long as it's
The
like
tester.
my week.
yeah, I'm trying to hear.
Is our bandit a new function supposed to work for dry diagonal, please?
Oh yeah, you said like p equal q equal 1, then it should function for that too.
It should work.
Yeah. Okay, so March 27th.
Yes.
You can
Okay.
go ahead and start crying for me now.
Okay.
Yeah, we scheduled all our other tests around your tests, so we scheduled our tests. Did you hear that?
Okay.
Yep.
I scheduled.
Yeah. Well, I promise you that Dr. Cole and I did not conspire.
Lies.
What a shame.
Okay. Well, I feel like it seems like faculty tend to accidentally conspire because a lot of them have the same number of tests and they try to break down as one to help them and they happen to fall at the same time. Okay. Let's see. So that's on the. Okay. Because right after spring break we have one more topic and review and then midterm. Okay. All right. I'll adjust. So we don't have all that hell all at once. Well, but it'll have to be later. Okay. Well, also, around that time, that last week of March, I'm going to have two graduate students, like one submitting a dissertation, one submitting a thesis, and I will probably be so preoccupied with them that I'll be not.
Yeah, the take-home midterm.
What?
Yeah, that'll work.
Yeah.
Be careful what you ask for.
Okay. Well, when I first started teaching this class here, I did give take-home assignments, and I think 6 students were pretty traumatized by them.
Well, I mean, I'm not saying that it'd be easy.
Well, yeah, I can assure you that it would not.
Well, we ain't waiting until April.
Okay. So I've not yet determined exactly what will go in the midterm. I do have some preliminary thoughts about that, and then if it's going to be in class, then I would want to put out a practice one. So I'm currently open to anything. So we'll just see how it goes.
I'll make the test, I got us.
Just let her make it. She seems qualified.
That's so funny.
I'm a teacher, I make tests.
Not this test.
I'll put stuff on there that I don't know how to do. That's a lot.
Well, I seriously think if we're going to go in that direction, I would probably be a whole lot more interested.
Hell no.
Hush.
That is a
Hush.
non-starter.
I'm sorry, that's great. I mean,
Okay.
We could do it that next Thursday. I mean, we were gonna have it on a Tuesday. We can have it on a Thursday.
Thursday the 29th, just both the 2 days.
That might help a little.
I don't.
I remember modern. I remember modern. Still got gray hairs from that
I'm
class.
just gonna put one.
We'll see.
We should just come to that bridge when we, cross that bridge when we come to it.
Okay. Anyhow, but yeah, I want to put on. But I can assure you that I'm not going to do this for the final. Now, last semester there was a written final, and then I gave students the option of I think it's done orally. I'm open to doing that in this case too. But yeah, I'm not going to do a take-home one for that. And trust me, you would thank me for that. Okay. Well, if you look, like for instance, like on my website, if you add a little bit, whoops, need to bring this back. Okay. Okay. Now that's just address for the class side, but then if you add something onto it, like spring of 10, also 14 and 16, so spring 2010, 2014, 2016 are the previous times I taught that class, this class. So you can see the take-home assignments or final projects that I gave, and see what you would be in for if I went that route. But so do that, then still see if you're interested in a take-home. But gee, I can't imagine who that would be. Yeah, but yeah. So you can ask your sister just how much she suffered from my take-homes.
I'm gonna have many stories to tell.
Yeah.
but on take-homes, I mean, we might get commutative algebras.
What is he even
Shut up.
Tia wrote a good book.
Yeah, I do not jump over that fence. Okay, are there any other homework questions of any kind? Yes.
So about the banded matrix, are we supposed to, the Q and the P, are they numbers or they are vectors? Because
Oh, but P and Q? Oh no, P and Q are numbers. They're indicating what the upper and lower bandwidth are. Because then your algorithm will take that into account in doing the row operations. Okay, so For that one, it's still a regular matrix. There's no vector storage.
Oh,
Yeah, that's for a different problem. Yeah, yeah, okay, yeah. I mean, yeah, so not very efficient, but yeah.
Okay. I actually thought it was vector, so I used the A as the main diagonal and the Q
Oh, I
as
see.
the
No, okay, yeah. Yeah, so this is a lazy banded LU factorization. Okay. Any other? Okay. All right.
The banded LU.
Yeah.
What I did was when I entered the third loop,
Uh-huh.
the third loop I had an if else statement because when I enter the third loop in the last column,
Uh-huh.
it should not like go to the if let's say I have a bandwidth of second,
Yeah.
I mean 2. When I enter the last column, it should not go to the second value of the upper bandwidth.
Oh, yeah. So you want to make sure to not go off the edge.
Yeah.
Yeah. Okay. Actually, that's something worth talking about, and I can show you an easier way to handle that than using an if statement. Okay. So, and I'll try to do it without giving too much away. So, for example, so what you're talking about is the innermost loop in Gaussian elimination, which normally goes from j plus 1 up to n, and then you do your row operation. Now, so the thing is, now you want to change that to take into account the upper or lower bandwidth, which is something you have to figure out. So, so what you can do to make, instead of using an if statement, you can do this. You can have your loop go from j plus 1 up to the minimum of n and whatever you would put there. So that uses a bandwidth. So that way, the loop is guaranteed to not go past the last column. I should point out that there is one other place within this algorithm where you also need to handle this. Because like when you're eliminating entries below the diagonal, again, you risk going off the edge. So the same idea can be used for that. Yeah. So because we have functions max and min, a and b will take the minimum or maximum of those. Okay. But yeah, so no, if you figure out the bandwidth, you put it in, and you still get an error, and it's like, okay. So another reason to make sure you guys run your code before you turn it in.
So if we use the minimum,
Yeah.
it won't like it will just take the minimum value
Right.
of the n.
Yes.
But in the other columns, it will take the maximum value.
Wait. I'm sorry. What do you mean by that?
I mean to say that in other columns except the fifth column, I need to.
Oh, like based on the bandwidth?
Yeah.
Yeah, so what will happen is, so if the bandwidth has you stop before n, that's where it'll stop. Because it's choosing a minimum of the two.
Oh, okay.
Yeah. So that way you're handling whatever entries you need to handle and absolutely nothing more. Okay. All right, let's we have some questions going. Are there any more? Okay. One comment I want to make also, as long as we're talking about assignments, about the quizzes. One thing, now, I know that some of you have gotten very adept at finding the right parts within the textbook that address whatever the question is about and slapping them in there. But it's also important that you take the time to understand what you're slapping in there, because I reserve a right to ask questions about those things on a midterm or final. So, because like when I see something that is just copy pasted from a book, it's also the wrong thing, as in not related to the question. Then it makes me think, okay, you guys are not looking at this closely enough, so don't do that. Okay, but especially, certainly for the final exam, like I know some of the undergraduates took differential equations from me 285, and also did it again in 460, where I had part of the test being like regular problems, and then the other part being what I call a lightning round, where I ask a bunch of questions about concepts. So I will do something of that nature this semester. So it's not just about running through problems. I will not ask MATLAB questions. So.
Good.
Oh, but MATLAB is so fun.
He can do MATLAB.
For everyone.
Give it to him.
Yes, there are 18 people in class. I'll ask you 18 times the MATLAB questions. Okay. All right. Anything more? I actually did not have planned to cover much that was new, but do something. But we're actually getting into a whole new chapter, and we are done with AX equals B. Well, okay. Actually, once you're in numerical analysis, you were never fully done with AX equals B. It's just it's no longer going to be our primary focus. So we're moving up from linear equations to nonlinear. Okay. So getting to chapter 10. Now, so the problem that we're going to solve now, like AX equals B, is very simple to state. So given some function f on some domain D, that's just an ordinary real value function, the kind of function you deal with like in calculus, and we're going to require that it's at least continuous, preferably differentiable also, but we won't require that. So we want to find some value that I'll call x star in the function's domain, such that f of x star is equal to 0. Okay. Now, you all know how to find roots for various simple categories of functions. Like college algebra, we're spending time solving quadratic equations, finding the roots of those. In your trig course, you occasionally had to solve trigonometric equations, like sine x equal to 1/2, something like that. But the problem is, in any experience that you've had of solving an equation f of x equals 0 by hand, whatever you were doing could only be applied to certain very narrow categories of functions. So it's this fundamental problem, fundamental just like AX equals B, that shows even better than the AX equals B case why we really need numerical methods. So I'm going to write down some equations that all seem alike, but in terms of how easy it is to solve them, are in fact very different. So suppose I have, for instance, okay, equation like that. Anybody, how would you solve that?
It's a quadratic equation.
Yeah, this one factors very nicely.
Yeah.
And if I change the numbers a little bit to something less nice, you could always use.
3 and a -2.
What?
Just factored it.
Yeah. Okay. Yeah. Easy peasy. So, or if the numbers weren't quite as nice, then
Quadratic formula.
quadratic formula. Yeah. Or if you're really psychotic, you do completing a square. But now I'm going to change this a little bit. Good luck. So,
Synthetic division.
what?
It's the next time.
Yeah. There's nothing you've learned in any class, unless something that I'm about to cover is explicitly covered in calculus, that would enable you to solve that. So just don't bother. I'll throw another one in there. Like, okay, one I mentioned earlier, sine x is equal to 1/2. How would you solve that one?
Unit circle.
All right. Can anyone give me a solution?
45 degrees.
No. No unit circle. What? Pi over 6. Yeah. Or 30 degrees. So then you can use symmetry or periodicity if you wanted to describe all solutions. Okay. So, all right. So the point is, although if I change this angle a little bit, or this value, instead of 1/2, as I said, sine x equal to, say, 4/5, you'd be like, I don't know. So, or if I did something like this, x sine x is equal to 1/2. Again, hopeless. There's nothing you've learned in any class that would enable you to solve that kind of equation. So the bottom line here is we cannot solve these equations directly. It's not like Gaussian elimination, for instance, where you have some finite sequence of steps that's going to magically lead you to a solution. So instead, what we're going to do is what we've just been doing with ax equals b. We're going to solve by iteration. So we're going to generate a sequence of approximations to x star, and try to improve these approximations and get a sequence that will converge to the exact solution. So then, after we stop at a certain point, we can say, okay, at least we're close enough. And maybe we can plug it into f and see, oh, we get this really small value. And there are several such approaches that we're going to see in this chapter, which we're going to spend a fair amount of time on. Okay. So, let's describe a general idea. Is we'll generate some sequence like x1, x2, whoops, we're not vectors, not yet anyway. Such that, hopefully, the limit as k goes to infinity of these iterates is equal to x star. Now, the goal is, in this case, we're just looking to find a root. Now, we have some functions that have infinitely many roots, or like polynomials of degree n have n roots. And if we can find all of them, that's great. But we're just going to focus on just finding some solution. Okay. Now, so that's one thing, is we want to find something that converges. And we're going to see cases where this sequence of iterates fails to converge. We have to be very careful, unfortunately, these methods. So, unlike ax equals b, if your matrix is not singular, you can definitely get a solution. But in this case, perhaps not, even though there is one. Okay. Now, so one goal is, of course, we're interested not just in accuracy, but also efficiency. Now we want xk to converge to x star as rapidly as possible. Now we're going to see a variety of methods. Some will be faster than others. So to describe convergence, we need these terms. So suppose we have some sequence of iterates, x labeled as xk. Just like for iterative methods, I just use this superscript. That converges to a limit. So if we know it has a limit, then to describe a convergence, we use the term order of convergence. So the order of convergence is some positive number r that has this property, that in the limit, if we look at the error after k iterations divided by the error after, k plus 1 iterations over the error after k iterations raised to the r power. And that should have a limit. It should converge to some constant. Okay. So another way of putting this is the error after k plus 1 iterations is proportional to the error after k iterations raised to the r power.
It says the limit of x to the
Oh,
down, that one, up,
as
that one.
xk plus 1, yeah. Funny. Okay, so what does this order of convergence mean? I just told you that it's proportional to a previous error raised to a power. Now, what we like to have happen is we want r to be larger, preferably. Because let's suppose if this error is already small, but then we raise it to a power greater than 1, we square it or we cube it. That means the next error is going to be far smaller. It'll go to 0 very rapidly. Okay. Now, I need to describe the various types of convergence that we can expect to see. But also I need to define another term. The value c, this limit here, is a name. We'll call it the asymptotic error constant. So that is also important when it comes to measuring error. Okay. All right, so types of convergence that we most often see is if r is equal to 1 and c is strictly between 0 and 1. So that is called linear convergence. So that's the kind that we'll most often see. Now, given this relationship, if I fill in r equal 1 here, so in other words, each error is proportional to the previous error, can anyone tell me why it is absolutely essential that this constant c be less than 1?
When you take the limit,
Uh-huh.
the x to the power k plus 1 minus x star, that's a fraction.
Yeah.
And it is divided by to the power of something. So which means if that power is 1, if we cancel, we get something like 1. So the fraction has to be less than 1.
That doesn't quite capture it though. Like, it might be easier looking at this to see. Imagine if c was greater than 1. What would go wrong?
You're getting more errors.
Yeah, the error gets larger. Not yeah. We need the error to be going to 0. So okay. Yeah. So that's the problem. To be guaranteed to be sure that the error will actually decrease, we need C to be less than 1. Now notice I omitted the case where C is 0 because you think, oh, C equals 0. You'd love to have that, and we do like to have that, but that's not linear convergence. So if R is equal to 1 and C is equal to 0, or if R is strictly between 1 and 2, that is called superlinear convergence. Or as one faculty member here once said, superlinear. I kid you not. So that's a situation where this ratio of errors is actually going to 0, so it's going to be somewhat faster. We will actually see a method that has a superlinear convergence. In fact, the R is equal to the golden ratio, 1.618. But even better would be if R is equal to 2, that is called quadratic convergence. We will see a quadratically convergent method. So what happens in that case is, like, the number of correct decimal places roughly doubles from one iteration to the next. So you see your error go from 10 to the minus 4 to 10 to the minus 8 and then 10 to the minus 16. And what that means is very few iterations are therefore needed, because at some point your error is going to be like a level of round-off error. And so those methods are lightning fast. We love that. We can have even faster convergent, more rapidly convergent methods. We could have cubic. There are methods like that out there. We won't really get into them because they have their drawbacks, actually. But these are the most common kinds. All right. Now, one other term that I will define is, in the case of linear convergence only, so this number, which is, I'll make sure I get it right. Okay. It's not one of my most commonly used definitions. Bless you. Okay. So rho is defined to be minus log to base 10 of C is the rate of convergence as opposed to order. So order and rate of convergence and rate of convergence are two entirely different things, but related. And the interpretation of that is that rho is the number of decimal places that are gained per iteration. Okay. So for example, let's suppose that C is equal to 0.01. So each error is 1/100th of a previous error. Well, in that case, rho would be equal to, it's minus log of 10 to the minus 2. So rho ends up being equal to 2. That means you gain 2 new decimal places per iteration. So that's a particularly fast kind of linear convergence. But a lot of times, rho is less than 1. For example, suppose C is equal to 1/2. Then you're not really gaining. It takes you a few iterations, like 3 or 4 iterations, to gain 1 decimal place. So that's actually kind of slow. Okay. Now, we're not going to get into we're not going to get into specific methods just yet, and we're low on time anyway. But what we'll talk about during what time we have left is fundamental questions about this problem, like existence or uniqueness of solutions, and also sensitivity. We have, if our H equals B, A can be ill-conditioned, this problem can also be ill-conditioned. All right, now existence and uniqueness I can talk about very quickly. Unfortunately, there's not much we can say. The easiest way to guarantee existence of a solution, a root of a function, is by the intermediate value theorem. From you would have seen in Calculus 1. And the intermediate value theorem says that if f is continuous on an interval AB, then for any value y, between f of A and f of B, then there exists some value c in the open interval AB such that f of c is equal to y. So in other words, whatever values you have at f of A and f of B, f is going to assume every single value in between, at least once. There's no getting around it because it's continuous. That's essential. So what that means is, if f of A is positive and f of B is negative, or if the other way around, doesn't matter. The point is, there's what?
I said you're guaranteed a 0.
Yes. So as long as you have a sign change, then there is a solution somewhere in AB. Now, there may be more than one. We don't know. So that our first method that we're going to see, method of bisection, on Tuesday, we'll use this idea. And the nice thing is, because you're guaranteed a solution, that's one thing that's very nice. A lot of times you're not guaranteed a solution. Okay. Unfortunately, that's pretty much all we got as far as existence. One thing I can say about uniqueness is called the inverse function theorem. And what that says is, if f prime is non-zero at a point, x naught, then the equation f of x equals y has a unique solution for all y that are sufficiently near f of x naught. Another way of putting it is that f is locally invertible. So it's like a one-to-one or invertible function near x naught. So in fact, when f of x naught equals 0, that can pose some problems. So I need to classify the kind of roots that we can find. All right, so types of roots that we can have is a simple root. These are our favorite kind, they're easiest to compute. That's where the function is equal to 0 at a point, but its derivative is non-zero. Those are best for numerical methods, for reasons that we'll see later on. Now, a multiple root, in other words, a root that has multiplicity m greater than 1, means that you have f of x star and f prime of x star and so on, all the way to the m minus first order derivative are all equal to 0. So for instance, if it's just f and f prime, that's a double root. F prime and f double prime, that's a triple root, and so on. And we also say that f is degenerate at the point x star. Okay. So these can cause, so multiple roots, even double roots, can cause real headaches for numerical methods. Now, yes?
In the exponent with your last f next to x star equals 0, is that m plus 1?
M minus 1.
M minus 1.
Yeah, so we have m items altogether that are 0. Now, when f is a polynomial, that means you would literally have x minus x star to the m in the factorization. But to hope this idea of multiple roots applies to non-polynomial functions also. Okay. So like you can like partially factor it. Okay. Now, so now what I'm going to do is I'm going to explain using graphs why simple roots are nicer to work with. That leads to a well-conditioned problem as opposed to multiple roots. Okay. Well, actually, before I get to the graphs, we have a simple equation to work with. So this is a concept that was covered last semester. The condition number not for just x equals b, of the problem of computing y equals f of x is approximated by the absolute value of f prime at x. So the derivative of a function, whatever you're trying to compute, is a good indication of conditioning. So the larger the condition number, the worse the conditioning of its problem is. So we like small condition numbers. Now for root finding, we're not computing y equals f of x, we're computing x. So our output is x star, which is playing the role of y, is f inverse of 0. Because f of x star is equal to 0. So it's not f we're computing, it's f inverse. Therefore, the condition number is not f prime, it's a derivative of f inverse. So it's a derivative of f inverse of x at, actually you can use y here, at y equals 0. Now, in case you don't remember how to take the derivative of an inverse function, I'll refresh your memory because I think we don't cover this in our calculus sequence at all, which is kind of bad. It's 1 over f prime at f inverse of 0. So in other words, 1 over f prime at x star. So you look at the derivative at the root. If the derivative at the root is small, that's a very badly conditioned problem. If it's equal to 0, then it's hopelessly conditioned. That should be like an actual term. Okay, so actually I need to take absolute value of all this. Okay, so now I'm going to explain using graphs why there's such a problem with ill-conditioned. So first, the well-conditioned case. Okay. I know I'm almost out of time. So the well-conditioned case, you have a situation like this where we have f prime is fairly large. So 1 over f prime is fairly small. So here's your root x star. So what happens is I can have a value of f of x hat. Like, suppose my approximate solution is x hat here. F of x hat is relatively large, but the error I should say the small forward error, which is the error we really care about, that is small, whereas the backward error, which is f of x hat, is relatively large. That's a good thing. It's a forward error we want to be small, at least small relative to the backward error. So in other words, we could find a value of f where it's still not all that small, it's not all that close to 0, and yet we're still really close to the root, which is the bottom line here. So we like these kind of problems from a numerical standpoint. On the other hand, the ill-conditioned case, we have a function that is very flat near the root. So something like nearly a horizontal tangent. So let's suppose my approximation is this, x hat, right here. So right here, f of x hat is very small, very close to 0, but the actual error we care about, x hat minus x star, is large. Okay, so in other words, we think we're getting close to root because we're plugging our approximations into f hat or into f, and we're saying, oh, the values of f are nearly 0, so we must have a root. Well, actually, no, you're not even close. And what we'll see is that when we cover actual methods, that's supposed to be an arrow, not a freaking check mark or Nike logo. When we get to numerical methods and we see what nice properties they can have, if they have nice properties to begin with, that if a function has a double or multiple root, those properties fail, and we end up, the method might still work, but it won't work nearly as well. So something that seems like a very simple problem to describe, find out where f of x equals 0, can actually be an extremely difficult problem. And there are things we can do to work around it. But okay, so, whoops, sorry, 1 minute past time. But we did start 8 minutes late, so.
Well, that sounds like we got a whole 8 minutes left.
Yeah, and I know that those of you taking prob and stats, that you'll have such important material from the get-go. So you better hurry up and get over there before you miss anything. I'm sorry. No, I'm not. Okay, so on Tuesday we'll start seeing specific root finding methods. Okay.